Everyone, welcome to all of you in my lecture today. So in this lecture I am going to discuss about the previous year question of heterogeneous catalytic reaction system in GATE chemical engineering. So let's start with the question first. The question says that the fresh catalyst is loaded into a reactor before the start of the following catalytic reaction. So a catalytic reaction is happening here and the fresh catalyst is being used initially. So first the reaction is given as A is getting converted into the product. The catalyst gets deactivated over time. The instantaneous activity AT at time t is defined as the ratio of the rate of reaction minus RA dash at time t to the rate of reactions with fresh catalyst. When fresh catalyst is used, so let's say when fresh catalyst is used, minus RA dash or RA dash will be equals to at t equals to 0. Is that clear? So minus RA dash at t, which is given as minus 0.5 t plus 10, right? So at t equals to 0, minus RA dash, at t equals to 0, minus RA dash when t equals to 0 can be written as minus 0.5 multiplied with 0 plus 10. So that will give you a value of 10. Now minus of RA dash at t equals to 10 hours, that will be equals to how much? Minus 0.5 multiplied with 10 plus 10. So that will give you a 5. So what is AT? So activity of the catalyst AT, that is minus of RA dash at t equals to 10 from the problem. Here it has been given t equals to 10 divided minus RA dash at t equals to 0. So that will give you 5 divided by 10, that is equals to 0.5. So the activity of catalyst for this particular problem will be equals to 0.5, right? But this was a new concept, that has been introduced in heterogeneous catalytic system. So this kind of question you will see in the Fogler book. So you can go and you can solve some more questions from there only, right? Okay. So I hope this question is clear to all of you. Now I'll be moving towards the next problem of today's discussion. The question says that a a reaction A is getting converted into B is carried out isothermally on a porous catalyst, right? So just one second, yeah. So porous catalyst is there and the intrinsic reaction rate is given. So minus of RA, which is given as kCa square, where K is the rate constant, C is the concentration of A. If the reaction is a strong pore diffusion control region, so when we talk about for a strong pore diffusion control region, you can say that N observed, that will be equals to N true plus 1 divided by 2. Is that clear? N true plus 1 divided by 2. So what is N true here? N true is your 2. So what is N observed? That is equals to 2 plus 1 divided by 2, that is equals to 3 by 2. So from this particular solution you have got the answer will be your 3 by 2. So your option C will be your correct option, right? So here the thing is that you have to remember this formula. So if you are able to remember this formula, then the thing will be very easy for you. And this formula is only valid for the strong pore diffusion control region, right? Okay, so now I'll be moving towards the next problem of today's discussion. So this question is also very, very important. So this kind of question was a very new type of question that has been asked in the GATE. So here in this problem you can see that ethylene absorbs on the vacant site V of a transition metal catalyst according to the following reaction mechanism. So you have given C2H4 plus there are two vacant sites that will give you this C2H4 and VB. So if NT, NV and C2H4 denotes the total number of active catalysts or active sites, number of vacant sites and number of adsorbed C2H4 molecules respectively, the balance on the total number of active sites is. So just try to understand, when we talk about C2H4 molecule, this C2H4 molecule look like in that way. there is H, H, H and H. So if I will able to break this bond, so these molecules will be looking like that. So there is H, H, hydrogen will get attached here. But now you will see these two vacant sites are there here. So any molecules can come and get a job here for the reaction. So if I am talking about number of active sites for these molecules, number of active sites for C2H4, that will be equal to how much? 2 multiplied with number of sites for C2H4. This one is given to you. And how many number of vacant sites will be equals to number of will be equals to NV. So what is total number of sites? That is equals to number of vacant site plus 2 into number of sites due to C2H4, because for one C2H4 molecules 2 empty sites are available, right? So I hope this will be your answer. And again, this question was a bit tricky kind of question, because you have to understand the molecules first, and once you understood the molecules, you can understand how many number of molecules can come and get attached with that particular molecule. So with that, you can see your option B will be your correct option. Is that clear? Okay, so great. After that, I'll be moving towards the next problem, and the question says that a catalytic gas phase reaction P is getting conducted in an isothermal packed bed reactor. So you are having a packed bed reactor, something like that. So you can see in packed bed reactor, the packing material used to be like that. Okay, this one is the packing material, and when this reaction will happen, the reactant molecules will be entering from this side, let's say, and this is coming out of this reactor from here. So the packed bed reactor, the reaction is irreversible and second order. So let's say P is getting converted into Q and Ne will be equals to 2. This reaction is irreversible. The feed is pure A with volumetric flow rate. Volumetric flow rate here, that is given to you, that is 1 liter per minute, and concentration of A at the inlet of the reactor Ca0 is also given to you, 2 mole per liter. So again, you have given the additional information for this particular problem, that assumptions that you can take is the reactant and product are ideal gases. There is no volume change associated with the reaction. There means this is a constant volume reaction system, and the ideal flow condition prevails in the packed bed reactor. So the design equation that we generally use in a plug flow reactor can be used for the packed bed reactor also. Okay, so now here they have given you that when the mass of the catalyst is in the reactor is 4 kg. So mass of the catalyst is given 4 gram. In the concentration measured at the exit is, and the concentration at the exit of the reactor is 0.4 obviously mole per liter. The second order rate constant, so you are supposed to calculate the second order rate constant, right? So when we talk about for plug flow reactor in liquid phase system, what happens? V divided by V naught, that is equals to Ca naught, and 0 to Xa dxa divided by minus Ra. So this one is our design equation for plug flow reactor for constant volume reaction system, or design equations. But when we talk about for packed bed reactor, packed bed reactor, you can write W divided by V naught, that is equals to CO naught 0 to Xa dxa divided by minus Ra. So you don't have to write this step in the examination. So directly you can write these things. You should know the formula of packed bed reactor. So now first we can calculate conversion. Conversion is what? 1 minus Ca divided by Ca naught. So that is equals to 1 minus 0.4 divided by 2. That is 1 minus 0.2. So conversion you have calculated 0.8. Once you have calculated conversion, so what is the rate of reactions? Rate of reaction is K Ca square. Okay, K Ca square or if you don't want to write in terms of conversion also, so directly you can calculate in this way. So W divided by V naught, that is equals to minus 0 to Ca naught to Ca dca divided by minus Ra. So these equations can be written in this form also. So W divided by V naught can be written as minus integral obviously Ca naught to Ca and dca divided by K Ca square. Is that clear? So you can write directly W divided by V naught, that is equals to 1 by K, you can write 1 by Ca minus 1 by Ca naught. So W we know 4. Volumetric flow rate is also given to you. How much? That is 1 liter per minute. That is 1 upon K, and 1 by 0.2 minus 0.4 minus 1 by 2. So you can write 4 is equals to 1 upon K into 10 divided by 4 minus half. So that is equals to 4 equals to 1 upon K into 3.5 minus 0.5. So the value of K can be written as your 3 divided by 4. Okay, that will be equals to 0.75. So this one is the way that you can calculate this kind of problem. I hope this question is clear. This question was not very difficult. This is very simple question. After that, I'll be moving towards the next problem, and the question says that a liquid phase irreversible reaction P is getting converted into Q and P is getting converted into R, having rate constant is K1 and K2. That is happening in ideal CSTR. So this reactor is continuously stirred tank reactor where reactant will be coming and the product will be leaving out. A space time for the reactor is given, tau is equals to 1 minute, that is given to you. Both the reactions are first order reactions where P, K1, K2 denotes the rate constant for the reaction, and the conversion of the reactant P, so XP is given to you, that is equals to 0.6, and the selectivity of Q with respect to R is 50%. So selectivity of Q with respect to R, so RQ divided by RR, that is given as 0.5. So RQ is what? K1Ca, and RR is K2Ca, that is equals to 0.5. So from here you can calculate the value of K1 divided by K2, that is half. So K2 is equals to 2K1, right? So you got one equation, let's say. Second equation is that conversion. So conversion is XP is equals to 0.60, right? So what I can write, CP is equals to obviously CP naught or into so the conversion of reactant P is 60%. Is that clear? So yeah, so for if you want to write the design equation for CSTR, so can I write By V naught, that is equals to Cp naught XP divided by K1 plus K2 into Cp naught into 1 minus XP. Why? Because first order reaction is there. So V is given to you or tau is given to you, that is 1 minute, that is equals to Cp naught will get cancelled out, and XP is given to you is 60. So 0.60 upon K1 plus K2 you can write multiplied with 1 minus 0.60. So from here you can get K1 plus K2, that is equals to 6 divided by 4, which is 3 by 2, which is equals to 1.5. And K2 is you have got 2K1. So you can write here K1 plus 2K1, that is equals to 1.5. So 3K1, which is equals to 1.5. K1 is equals to 1.5 divided by 3, which is equals to 0.5. Is that clear? So from here you can calculate the value of K1. Okay, this question was not very tough. This was from ideal reactor condition kind of thing. Parallel reaction is happening in CSTR, but this is an important kind of question that you can understand. In future the questions can be asked. Now next question says that the liquid the square of Thiele modulus MT is given by MT square, that is equals to L square K divided by D effectiveness. So here Thiele modulus MT is used to be directly proportional to what? Reaction rate divided by diffusion rate, and since rate is inversely proportional to time, so directly we can write, so MT square will be directly proportional to that diffusion time scale divided by reaction time scale. Is that clear? This one will be your answer. So let's try to understand which of the following options will be correct for you. So time scale for the pore diffusion divided by time scale for reaction rate of, okay, so option A will be your correct, because this is the time scale for the pore diffusion divided by time scale for the reaction that we got also. Okay, now next question is that the for a first order reaction in a porous spherical catalyst. So you have a porous spherical catalyst. This spherical catalyst is given to you. Let's say, so in porous spherical catalyst, if you see that this one is the pore diameter, so if let's say if this one is the pore diameter, if diameter of pore, if pore diameter is large, then diffusion will be fast, right? Due to larger pore diameter, diffusion will be fast. Okay, first thing. Second thing, that here it is, it has been given in the problem that diffusion effects are most likely to lower the observed rate of reaction. So if diffusion is more, right, so obviously when diffusion will be more, when pore diameter is large. So pore diameter is large is there in this and in this option, and you have to be a slower reaction, then the diffusion will be fast. So that's why your option B will be your correct option. Is that clear? But again, if the question would be like if the diffusion effects are most likely to increase the observed rate of reactions, in that condition rate of reaction will be fast and diffusion will be slow. So when diffusion will be slow, when the pore diameter will be very slow. Pore diameter is small, then the diffusion will be very slow. That's why you can use option B is the correct, right? So again, various kind of questions can be formed here based on the pore diameter and reaction rate condition, but you have to understand what kind of mechanisms are there. Now next question is that 6.32. This question is also a good question. So you can say that hydrogenation of benzene is to be carried out using nickel as a catalyst, and there is a non-porous hollow cylinder as shown in the figure. The reaction occurs on all the surface of the hollow cylinder. During an experiment, one such cylinder is suspended in the reactant stream. If the observed rate of reaction is 0.3, so rate of reaction minus RA dash is given as 0.39 mole per meter square of the catalyst per minute, and you are supposed to calculate minus RA double dash in mole per kg of catalyst per minute. So how can we calculate? Just try to understand. So if I want to write minus RA dash, I can write divide that is equals to 1 upon SS into dNA by dt minus dNA by dt. Is that clear? And if I want to write minus RA double dash, that can be written as 1 upon W and again 1 by dNA minus dNA by dt. So let's say this one is equation first and this one is equation second. If I'll divide equation first by second, what will I get? I'll get minus RA dash divided by minus RA double dash, that is equals to 1 upon SS minus dNA by dt divided by 1 upon SS minus dNA by dt. So you can see this part will get cancelled out here. Finally you will left with minus of RA dash divided by minus of RA double dash, that is equals to, sorry, this one will be W. So W divided by SS. So we can say that SS multiplied with minus RA that is equals to W multiplied with minus RA double dash. Is that clear? Okay. So SS is given. So what is SS? SS is equals to pi d outer plus d inner multiplied with L. Why? Because reaction is happening like that. This is some porous catalyst, so reaction would be happening at this particular surface. So this at this particular surface, at this particular surface. right? That's why I'm writing P d outer into d inner into L. And what is W? W is equals to density into volume. And what is volume? Volume will be equals to pi by 4 d outer square minus d inner square multiplied with L. So that can be also written as pi by 4 d outer plus d inner, d outer minus d inner into L. So let's substitute all of these things here. So RA dash is given to you, that is 0.39. So 0.39 multiplied with pi into d outer plus d inner into L. That will be equals to density of the material is also given 8910. Is that clear? So I can write here 8910 multiplied with obviously pi by 4 into d outer plus d inner into d outer minus d inner into L multiplied with minus RA double dash, that we are supposed to calculate. So here you can see d outer, d inner, pi and pi will get cancelled out, L and L will get cancelled out. So finally you will left with minus RA double dash can be written as 0.39 multiplied with 4 divided by 8910 multiplied with d outer is 25 minus 20 into 10 to the power minus 3. So once you will calculate these things, you will get these things over there, and the unit of these things will be in mole per kg minute inverse, sorry, mole per kg minute. Is that clear? So this is how you can calculate this kind of problem. This is just a geometrical based question and nothing else. Now moving towards the next question of today's discussion. This will be the last question of this lecture only. So here in this problem you can see that in a laboratory batch setup, so you are having a batch reactor. All of these particular things will be happening in a batch reactor. There is no input, no output in the batch reactor, and this reaction is a parallel reaction. P is getting converted into 2Q and P is getting converted into R. At the end of 1 hour, the operation, the batch contains XP, XQ and XR mole fraction of PQR respectively. The mole fraction of product component were found to be vary linearly with the temperature. Okay, so here you can see the mole fraction is varying linearly with the temperature. So if I plot this curve again, you will see. So this one is the mole fraction X and this one is the temperature. So one graph is looking like that way. And another one is looking like that. Okay, so here you can see there are different temperature that is given, that is 25, 50, 75, 100 and so on and so forth, temperature in degrees centigrade. So at 25 degrees centigrade it has been given, at 25 degrees centigrade it has been given that the yield of Q based on the product, let's say yield of Q. So yield is XQ divided by XP, means concentration of P divided by concentration of Q, P, that is equals to 0.40. That is given to you. So you are supposed to calculate at 100 degrees centigrade what is the yield. So this one is your YQ. So what is yield at 100 degrees centigrade, right? So what is yield here? Again you can calculate XQ divided by XP. So at 100 degrees centigrade you are supposed to calculate these things. Let's try to understand how we can do these things. So if I am talking about at 25 degrees centigrade XQ divided by XP, which is equals to 0.40, right? But this curve, this line shows the mole fraction of XQ and XR. Is that clear? So if I am subtracting 1 minus XQ divided by XP, that is equals to 1 minus 0.40. So that will give you XP minus XQ divided by XP, which is equals to 0.60. So this is your XR divided by XP, which is equals to 0.60, right? So at 25 degrees centigrade, if I want to calculate XQ divided by XR, so that is equals to 0.40 divided by 0.60. So XQ by XR you are getting is 2 by 3, right? XQ by XR. Just try to understand one more thing here. If I am assuming this length is Z, let's say Z1. So this point At this point, this is at 25 degrees centigrade. This one will be your xq, and from here to here, this point will be your xr. So let's say slope of this line is m1 and slope of this line is m2. So at 25 degrees centigrade, can I say at 25 degrees centigrade, what is m1? m1 is equals to xq divided by z1. And what is m2? m2 is equals to xr divided by z1. So what is m1 by m2? That is equals to xq divided by xr. Is that clear? And xq divided by xr is your 2 by 3. Is that clear? 2 by 3. Okay. So this is xq and this one is xr. Now when we come to 60 degrees centigrade, I can go here and again I can go here. So at 60 degrees centigrade, if I want to calculate the slope of this line m1, so let's say at 60 degrees centigrade, what is m1? m1 will be here also. This one divided by, let's say if I am talking about this one is z2. Right. So xq divided by z2, and what is m2? m2 is your xr divided by z2. Is that clear? So if I am calculating m1 by m2, that is equals to xq divided by xr, and from here you can know m1 by m2 is 2 by 3, so that is your xq divided by xr. So m1 by m2 at this point is also 2 by 3. So slope, because slope is not going to change, this is linear line equation, or sorry, a straight line, right? So if you get to know xq divided by xr, so we want to find out xq divided by xp. So can I write xq divided by xp? That will be equals to 2 divided by 5. That will be equals to 0.4 here. Directly. So here also yield of q at 60 degrees centigrade, that will be equals to 0.40. Okay. So this question, in this particular problem, you can use two different concepts. One is your basically that is the yield concept, and another one is your the equation of a straight line concept. That's it, and nothing else was there, right? I hope this question was clear to all of you now. So with that, I'd like to end the lecture, and you'll see in the next lecture where I'll be talking about some more questions from the heterogeneous catalytic reaction system. Okay, thank you all.